This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 3303 solids, reviewing a recent test. And it's a shear flow problem. It's actually a shear flow and a shear problem. It's two problems in one. Starting with the discussion, I see, or the setup, I've got the T-beam is constructed from two boards with nails connecting them. The nails can support a shear force of 550 pounds. So before I go very much further, I want to go to my equation sheet and write down the applicable formulas so I can see what I know, what I don't know, and how to get there. So the formulas for shear flow, which are when we're building up shapes, in this case a beam, out of composite pieces, then I want shear flow to know what that force that's connecting them. And the formula for shear flow from the equation sheet, one of them is VQ over I. Then I got another equation that I don't really like the wording of, and the way it's put is that S is equal to V nail divided by Q. Well, I want to rearrange that, so I got that equals to Q also. So Q in this other equation is equal to V nail divided by S, the spacing. So I have to know what all those letters stand for. And so I don't really like V nail, so I prefer to call it the force per connector, F connector, which I'm given as 550 pounds in this problem. So now I want to equate little q's VQ over IT to force in connector divided by S. So I can say that is equal to VQ over I. And I want to rearrange that and solve for S. So S, just rearrange, is equal to F connector I divided by VQ. Now Q is the tricky one. It's the first moment of area, and in this case it's the first moment of the area of the piece that I'm connecting one to another. So Q from the equation sheet is equal to Y bar prime A prime. Well, A prime is the area of the piece being connected, which is the top board. Y prime is still the distance from the neutral axis to the centroid of A prime. From NA, the neutral axis, which is located for me on this problem, to the centroid of A prime. Okay, so let's work on Q first, which means working on Y bar prime A prime. Okay, A prime is the area of the piece being connected, so it's the area of this top board. So it's really just that little, I'm going to hatch it in. It's the area of that board. So A prime is equal to, it's 10 inches wide, it's 1.5 inches thick, deep, 15 square inches. Y bar prime is the distance from the neutral axis to that point. So the centroid of that board is right there, right in the middle of that rectangle. So that is, blowing it up as much as I can, it's half of its height. So that's 0.75 inches down from the top. It's also 0.75 inches from the bottom of the board. So I'm going to figure it this way. There's other ways to figure it. The overall height of the section is 10 plus 1.5, or 11.5 inches. And I'm given Y bar here, the distance from the bottom to the neutral axis, 7.88. Therefore, the distance that I want is that distance there, y bar prime, from the neutral axis to the centroid of the top board. So y bar prime, just working backwards into it, is 11.5, the overall height, minus the y bar for the distance from the bottom, 7.88 to the neutral axis, and then minus half the thickness of that board on top, 0.75. And that number works out to be 2.87 inches. Therefore, I can figure Q for the shear flow problem is those two numbers multiplied together. 15 inches cubed times 2.87 inches is 43.05 inches cubed. So that's the hard number to figure. The rest of them I'm given, so I can plug back into this formula that S is equal to the force per connector, which is given to me. Back in, let's review the problem. I got each nail can support shear force of 550 pounds. The shear force on the beam is 1.5 kips, and the centroidal moment of inertia, I, is 376. So I need all those numbers. So the force per connector is 550. That's pounds. I is 376. That's inches to the fourth. V is the total shear force on the beam, 1.5 kips. But for consistency, let's just call it 1,500 pounds. So I got pounds on the top and pounds on the bottom. And then Q is that number I just calculated, 43.05. That's inches cubed. So I got pound inches to the fourth on the top, pound inches cubed on the bottom. Pounds cancel out, inches to the fourth cancels out all but one. So I'm left with inches as the unit of my answer, which is what I want because it's a spacing. I run the numbers and I get S is equal to 3.2 inches. Okay, the problem, look at it, asks for me to give the spacing to the nearest quarter inch. So I can go up to 3.25 or I could go down to 3.0 inches. Now I'm trying to figure I'm trying to provide a shear flow of Q is F divided by S. So if I've got 550 on the top and I put a number of, let's say I go try 3.25. Well, that's going to give me a number slightly smaller, so it's less shear flow than what I really need. So if I go 3 inches, I've got 550 divided by 3, so the denominator is smaller, so I get a bigger number. So this is the one I want to use, 3 inches. So I report my answer as the spacing is 3.0 inches. Okay, that's the first part of the problem. Now I have a closely related but not identical problem for number 20. Determine the maximum shear stress in the wood. Okay, shear stress, unless I'm told I want average shear stress with V over A, I need to figure that shear stress is, due to straight line shear, VQ over IT. So I have the equation tau equals VQ over IT. I know my shear force, I know I can figure the thickness, that's the width at the cross section where I'm taking the shear stress. Q is a variable depending on where I'm taking the shear stress. Hopefully I know from doing homework problems and other things that the maximum shear stress occurs where the Q is max. So tau max is at Q max. Q max is at the neutral axis. So looking at my drawing and hatching in that. So what I have here is let me draw a line and separate these two problems so I don't get confused. Okay, in Q, A prime is the area away from the neutral axis at the point where I'm calculating stress. So I have two choices for Q in this case. I can pick the little T-shaped section on top, where that's the neutral axis. Or I can pick the bottom part, which is the web, just a simple rectangle at the neutral axis. Obviously, the bottom part is the easier part, because this is a rectangle. It's Y-bar tall, 7.88 inches. It's 1.5 inches thick. So for that thing, A prime is just 7.88 times 1.5. That number works out to be 11.82 square inches. And then Y bar prime is the distance from the neutral axis to the centroid of that shape. So that's just the distance right there, half of 7.88. Which is 3.94 inches. So Q that I'm interested in, which is Q max, those two numbers multiplied together. 3.94 times 11.82, and I get 46.57 inches cubed. I check it on this versus this other one for the board, 43.05, so it is bigger a little bit, and so I'm satisfied this is a good number. Now I'm just ready to plug and chug. Tau is VQ over IT. V is 1.5 kips. Q is that number I just calculated, 46.57. That's inches cubed. I is that number that's given to me, 376 inches to the fourth. And T is the thickness or the width of the cross section where I'm taking the shear stress. Well, that's just the thickness of that web, 1.5 inches. T is right there for this calculation, the width or the thickness, 1.5 inches. So I do the math and I get the shear stress, the maximum shear stress on the section is 0.1239. I got kips, inches cubed on the top, inches to the fifth on the bottom, so that gives me kips per square inch, which is what I want, a stress, so I got KSI. That's the stress. I can report it two ways, 0.124 KSI. If I was working in pounds on the top, say 1,500 pounds for V, I would get an answer that's in pounds per square foot. And there you go.